Assalamualaikum and good day everyone. So today we will continue last subtopic in chapter 6, single and double decrement environment. Okay, before this we just cover on single decrement, which is our event of interest only about death. So now we have double decrement, which is we have about death and withdrawal. Since this is incomplete data, so some subject leave the observation because of other event than death. So now we also want to cover x to x plus 1, the interval of x to x plus 1. So the interval x to x plus 1. So this is the entry h, x plus ri. This is the exit h. So in this case, the entry h and the exit h between x and x plus 1. So this is the period. So the period is from x plus si. I is referring to the subject, so we no need to write down the I. X plus s minus x plus r. So we get s minus r. So the period here is s minus r. Okay, now look at the probability of survive. So survive to age x plus s. So this is the period s minus r, since this is the period s minus r. So before this we are really familiar with TPX, which is the probability of survive until x plus t. So the time is t. So the time here is s minus r, just the period. We not consider the age. So the t is s minus r here. Okay, so this is probability of survive. So you are really familiar with this notation. And also we have probability of death, where the relationship between death, probability of survive and death is 1 minus p, and we'll get qx. Then, since this is the probability of conditional on being alive at age x plus r. Okay, so if we draw the timeline, so still the same timeline, x to x plus 1, so one interval. So we are looking for x plus ri to x plus si, the entry and the exit h. So the subject must survive here until x plus ri. The condition is the subject must survive until x plus ri. So we call it as conditional probability. Remember the PDF, this is PDF, is TPX mu x plus t. Still remember in actuarial math 1. So the PDF is the small tf TPX times mu x plus t. So since the current age is x plus r and our period is until t minus r, and the conditional probability is until x plus t, and the force of mortality is at x plus t, meaning that the death will happen until x plus t. So survive until here, and the death will happen between x plus ri and x plus si. So this notation is adequate, however, only if the study is being conducted in an environment in which death is the only random event. So before this, our random event is only one, about death. Now for both death and withdrawal as the random event. So now we have TPXD and TPXW. TPXD for death and TPXW is for withdrawal. So look at this. We have new notation here, 1 and 2. We have TPX with prime D for death and TPX with prime W for withdrawal. The prime meaning that the death not occur prior to age x plus t. Since our event of interest or our random event is about death, so the TQX is for death. So the contradict of the TQX is the TPX. So we do not use the term survive anymore, but we use the contradict of the term of death. So death not occur prior to h plus t. So just the same thing, but we want to use we want to make it more clear. So same as the withdrawal. So the contradict probability of withdrawal is the TPX. So we use not occur prior to hx plus t. So prior to meaning that before h plus t. Still the same thing, but this time we use different term and different notation. Okay, so remember TPX. Recap, the TPX is equal to exponential -0 to t mu x plus u du. So remember last time we learned in actual math 1. So t, the upper bounds for the period. We also can write down as e the power of both are same. We also can write exponential like this form or this form. We are familiar with the second form. So the difference between TPX and TPXD, the mortality, the force of mortality. So this one, we use mortality just for death. It's for general form. And this is one for only death, for the decrement of death. Okay, so the relationship for QXD also 1 minus PXD prime. Same to the withdrawal. So for withdrawal, we use force of mortality for withdrawal. We use U here since we do not want to get confused with the upper bound here, T. Just the variable. Before this, we always use x plus t. So this time we use x plus u since we do not want to get confused with the upper bound, the t for upper bound. So okay, just the same thing. So the TPX tau includes all the random events. So for this situation, we have death and withdrawal. So TPX tau equal to TPX for death and TPX for withdrawal. So this is the probability neither dying or withdrawing prior to hs plus t given alive and not withdraw at h plus at hx. So if we draw the timeline, so must alive until here, and also the probability they are constant on x to x plus t, which is not dying and not withdrawing. So we are constant on probability from x to x plus t, which is the individual is not dying and not withdrawing, with the condition of survive until age x. The PDF for death is TPX mu x plus t, but we use TPX tau because this individual must not dying and must not withdrawal. So the force of mortality we use for D, the difference. So PDF for withdrawal, still we use the TPX tau, but we use force of mortality for withdrawal. So this one for general form, and this is this one for our case where we use T equal to S minus R, as I show you in the timeline before. So the PDF, if we use this, in this case the PDF is this one. This is PDF for death and this is PDF for withdrawal. So QXD is probability death prior to hx plus 1 for one interval. So this time we just look at for one interval. So t is equal to 1 in the presence of other decrement, and also qx for withdrawal, also probability of withdrawal prior to hx plus 1 in the presence of other decrement. So now we will solve okay, one more important for this relationship. Px tau is equal to Tpx for death and for times Tpx for withdrawal. But Tqx tau, we cannot directly times the probability of death. So this one just for Tpx tau. But for TQX tau, we cannot use this one. Okay, so how to find the TQX tau? So we use this formula. Or you can find TPX tau first, and then you just minus 1 minus QX tau is equal to 1 minus TPX tau. It's more easier. I recommend that way. So now we try to solve example 7. So example 7, given that if Qx for D is 0.1 and Qx for W is 0.2, find Qx tau. So remember, we cannot straight away times Qxd and Qx withdrawal like the probability of survive, the TPX. So how to find that? So Qxd meaning 0.1, it represents probability of death will occur prior to or before age x plus 1. So Qx prime for W is equal to 0.2, meaning that probability of withdrawal will occur before or prior to age x plus 1. So Qx tau, how to find the Qx tau? So Qx tau is equal to 1 minus Px tau. So this is for one interval. So how to find Px tau? Px tau is equal to Px prime for death and Px prime for withdrawal. So how to find Px time for withdrawal? So Px time withdrawal is equal to 1 minus Qx prime withdrawal times 1 minus Qx prime for withdrawal. So we substitute the value so we will get equal to 0.72. This is Px tau. So to get the Qx tau, we just use 1 minus Px tau equal to 1 minus 0.72, and the answer is 0.28. Okay, now we look at example 8. If the force of mortality given by mu xd is this one, this function, and mu x for withdrawal is this one, find the conditional density function for death at age 70 plus t given alive at age 70. So how to transform it? So the conditional density function, if we write in terms of notation, it becomes TPX tau times mu x plus t. So we have D, and we also have for withdrawal, we have force of motive for withdrawal. So we have to find both. So x is 70 plus t. So given that alive at age 70. So we are given in terms of these two functions. So first we have to convert the force of mortality into we convert it in terms of the in terms of this age. So 70 plus t. So we have to change the function in terms of 70 plus t. So we substitute x with 70 plus t. And we will get 1 over 320 minus t. So this is for death. And second one, for withdrawal. So for withdrawal, W is equal to second function 2 over 390 minus, so x we substitute with 70 plus t. So it's equal to 2 over 320 minus t. Okay, now we can find TPX tau. So TPX tau is equal to, so x is 70, because given that this individual must survive or alive until age 70. So 70 to 70 plus t tau equal to prime for death times for withdrawal. So how to find t? So we use exponential 0 to t. So remember, I put in green color last time. So mu 70 plus t, because this is for withdrawal, so we use for withdrawal du. Sorry, we use u here. So u here. So we solve for this one. So we substitute. This is 1 over 320 minus, since we use in terms of u, so we put u here instead of t du. So we will get ln 20 minus u times negative 1 from 0 to t and we solve for the ln, substitute the boundaries, and the answer is 20 minus t over 20, the power of 1/3. Then we find for TP 70 prime for withdrawal. So we substitute force of mortality for withdrawal, and then we solve for this one, and we get 20 minus t over 20, 1 over 2/3, sorry, 2/3 here. So we will get 20 minus t over 20 power of 2/3. So now we can find TPX tau by multiply TPX tau for death with TPX for withdrawal. So we get 20 minus t over 20. So now we can find TPX for death, where we times TPX tau times with the force of mortality. So we substitute TPX tau is 20 minus t over 20 times force of mortality for death is, so we solve it and we will get 1 over 60. So we cancel out this one. This is PDF for death, and now we find PDF for withdrawal. So same, we use TPX tau as well, but this time we times with force of mortality for withdrawal, and the answer is so the answer is 1 over 30.